So it's Wednesday, and we're going to start with second order differential equations. But before we dive into the second order ones, let's solve the problem from last time on the board so we can get a handle on how to do it. That is, how to use the superposition principle to solve linear differential equations. And we had a differential equation that looked like this. And how was it then, Søren? Did it say y prime plus 2 times the equal to x squared plus 1 plus k snus to 3 times plus 8? Yes. So this is our differential equation. And one immediately sees with trained mathematical eyes that it is a first order differential equation, because what we are looking for is a function y, which depends on x. So we are searching for y equal to y of x. So that if you differentiate y with respect to x and substitute it there, and then take it unchanged and substitute it there, multiplying by 2, it should yield this function for any value of x. So all of this over here, that's actually what we usually call g of x. And that whole thing there is what we typically refer to as f of x when we use the general formula. But the challenge is that if you use the integrating factor formula, you get some quite challenging integrals. And that's why we looked last time at how to guess the solution in multiple steps. Namely, we know that when a differential equation is linear, it adheres to a solution structure. The complete solution to the differential equation is equal to a particular solution to the differential equation plus the complete solution to the homogeneous version of the same differential equation. So we utilize that solution structure, which we know the solution adheres to. That means if we can find the solution when the right side is only this. So if we can find a solution for that, and then afterward find a solution if the right side was only that, and finally find a solution if the right side was only that, well then we can add it all together, says the superposition principle, then we get the correct solution. So that's what we're trying to do. So the first thing we can do is find the complete solution to the homogeneous version of the equation. And what does the homogeneous version look like? Well, it's simply this. Y prime plus 2, y prime equals 0. It's homogeneous because it equals 0. And we have learned that to find the solution for it, the complete solution for the homogeneous one there, one should simply say a constant k times a to the negative integral of f. Can you remember it from last time? Yes. And we did that fairly quickly because that is f, and the antiderivative of a total is 2x. So 2x must be there. So it becomes k times e to the minus 12x. So far, so good.
Now we are down at the place.
1/4 of the task. Now we have the ingredient that should be included in the complete solution. How many components should be here? 3. Namely, a particular solution to the differential equation that arises if only that term was present, plus a particular solution to the differential equation that arises if only that term was on the right-hand side. And finally, the one that results if only that term was there. So we take it step by step. Here comes step 1. So we now assume it says y prime plus 2 times y
is equal to x squared plus 1.
And then we see if we can find a particular solution to that. What we do is guess a function of the same type as the right-hand side. And we see that the right-hand side is a quadratic polynomial in x. And therefore we guess corresponding to step 1. We guess that a particular solution for it could be found using this function type, ax squared plus bx plus c. For it is, after all, a general quadratic polynomial. There was another marker that was just as bad. Let's see if there's one in here.
This one is a bit better. We'll throw this one away.
Now I have learned from Christian that you should throw away the old markers. So if this is to be your solution, then I should be able to insert it into the differential equation and make the equal sign true. What does that mean? Well, it means differentiate yp and put it in y's position. Leave it untouched and place it in y's spot, and see if you can make it equal x squared plus 1 for all x values.
So I'll just find the y mark, yp mark.
And it's easy, because when I differentiate this, I get 2ax plus b. since that's how you differentiate ax squared plus bx plus c. So now I insert this into the y prime place. So I get 2ax plus b plus 2 times y, but y was x squared.
Plus b times x plus c.
Like that. And I need this to equal x squared plus 1 for any value of x. And note that the last thing I say is important for any x value, because when we calculate this in a moment, it turns out to yield a second degree polynomial. And this is also a second degree polynomial. And if two second degree polynomials are to be identical for every value of x, then all their coefficients must be identical. Otherwise, they cannot yield the same y value for every value of x. So what do we get when we calculate this? Well, we get 2x squared. If I start with the highest occurring power of x, and then I get 2bx here, but I also have 2ax here, so I get a total of 2a plus 2b, which is multiplied by x. Can you see that? Because from here came 2a times x, and from here came 2b times x, and that's what is written here.
And finally, I have 2c plus b.
And all that should yield x squared plus 1.
And now we are making use of
So the coefficient that is here, which is a 1. Here there is a hidden 1. It must match with this coefficient, which is the coefficient of x squared over here. So 2a must equal 1. So we conclude that 2a must equal 1, so it must be 1/2. So far, so good. The next thing we conclude is this, and now I better choose another color to make it a bit more illustrative maybe. So this coefficient here that stands with x to the first power, which is here. What should it then yield? It should yield 0, because on the right side, there's a hidden plus 0x. So because it says 0x, and here there's some x, that has to match that number. So this means that 2a plus 2b must equal 0. So 2 plus 2b must equal 0, but I already know that a is 1/2. So here it says 1.
So here it says 1 plus 2b.
Now I can find b, it must be negative 1/2. So here I find that b must be negative 1/2.
And finally, I can see that 2c plus b must equal 1. 2 times c plus b should be equal to 1.
But I've already found b. It was negative 1/2. So I substitute it in there. So it says 2c minus 1/2 must equal 1. And if I want to find c, I move the half over.
And then divide
so
by 2.
It becomes 3/2.
Then it says 3/4. So c should be 3/4. So now I have found both a and b and c. So we get our polar solution.
It belongs to step 1. I might call it yp1 maybe. It will become half x squared
minus 1/2 x.
Okay, thanks here. So far, so good.
Now I've found 2 out of 4 ingredients for the final solution.
So let's move on and imagine we are looking at the differential line code.
Y symbol plus 2y is case.
Let's take x. So y prime plus 2y equals cosine of 3x. I had already solved that for you, I believe, on the video. So we won't do it again. You can just tell me. What was it that we got?
I guessed this in step 2. I am stepping 2.
That's where we guessed that yp2, it should be some number like multiplied by 7 clothing x plus some number b times cos of 3x. So I explained how to do that in the previous recording, and then we found a and b, so we don't need to repeat that. And wasn't it something like 3/3 and 2/3? So that means now I can't remember which one was supposed to be 3/3. Was it a? A is 3/3, so I need to write 3/3.
Sine of 3x plus 2/3. Mix nuts up to 3 times.
So this here is the next ingredient in our solution. And then we are basically only missing 1. We only need to look at the equation y prime plus 2y equals e to the x.
So here comes step 2.
So I look at y prime plus 2y equals e to the x. And then my guess at step 3, that is the particular solution, yp3. It is called some number a times e to the power of x. And I'm just reusing the symbol a. Of course, that a has nothing to do with that other a. And that a also has nothing to do with that a there. It's just a new a. So it's reusing symbols. And just like before, I need to differentiate it and substitute it in there. Take it unchanged and put it there. And see if I can make it equal to e to the x for any value of x. So if I differentiate this, it will say that y prime 3 equals a times e to the power of x, because it differentiates and yields itself.
So the ax people will be standing there.
When I place one there, you then have to put plus 2 of e to the x, and over here it says e to the x. So we see that we can divide the equation by e to the x, because e to the x is never 0. We can divide by it. And when we do, it cancels out here, here, and here, leaving it at
Plus 2a should give 1.
But then 3
it
should
becomes 1. So I have 3 times a must equal 1, and therefore a must be 1/3. And now I can write up the entire solution to the original differential equation. So what is it then? The complete solution to the original differential equation is first the homogeneous k times e to the power of negative 2x. And then we need the one that comes from the attack polynomial, the one up there. So plus 1/2 x squared. Now I'm running into space issues, minus 1/2 x. Now you will see that my writing size approaches 0.
a half of x plus 3/4.
And then I need the one that includes sine and cosine, that is plus 3/13. Cosine of 3x
And plus 2 3/8. The rate is 2 times.
And finally, I need this 1/3.
It is genuine, and then it's done. Here is the complete solution. This is the final answer for this differential. So the trick with superposition is that you simply solve it a bit at a time by guessing functions that resemble those on the right side. It's certain. The question was who you might be asked to solve for on an exam one day. One like that would be annoying, and asked at an oral exam. But I won't do that, as I'm not that mean. However, you are expected to be familiar with the technique, and you might be asked y prime plus 2y equals, and then some first degree polynomial. You should be able to handle that in your head if I've made the numbers nice. But it's always difficult to do calculations in public. So what we are testing is not so much whether you can calculate, but whether you have understood the principles and ideas of the solution strategy. So it's much more important that you can explain that to us. And that you can explain in words what the superposition principle is. And then you can have prepared an example from home that you show, where you know you can solve it. But you should be prepared for some questions, but not very difficult ones. I usually think about what questions I wouldn't like to be asked myself, so I try to avoid asking any that are too tricky. So that was essentially the conclusion of our theory on first order lines and differential lines. And now we will hear about second order. And I am thinking of starting with an example from physics, so you can see what it can be used for. And then the theory afterwards.
So if we now call this board 1.
Once you've taken the picture, we can go to board 2 if anyone needs the picture.
All right.
I don't think it matters, but you can close it if you
Okay.
want to see. I think it continues recording independently of that.
Okay, so today we are starting on second order differential equations.
And fortunately, these are second-order lineages.
The battle lines we are opening.
Because some of them can be solved.
The course is designed in such a pedagogical way that we start with what we can actually manage, and we are only given what we can solve. And where does second order appear? Linear differential equations appear in nature in many places. And here comes probably the most important example in all of physics. This is the most important physics example I have seen. It is called the simple harmonic oscillator, and it's something that oscillates. So we need to take a look at something called simple harmonic oscillation. And that is in fact a second order differential equation.
Simple, harmonious.
Oscillation, I just call it oscillation because I can't remember how to spell oscillation. So we avoided making spelling mistakes with that. So what is a simple harmonic oscillation? Where are they? Everywhere.
Then my creation.
A temporal pressure propagation in the air. It spreads through the air, that pressure variation, and makes your eardrum vibrate at the same frequency as my vocal cords. So I can embed intention into the frequency, and your ears can detect and interpret it as language and information. That is an example of simple harmonic oscillation. It can also be a pendulum. If you have a string with a mass, and you pull the string to the side and let it go, it will swing back and forth like this. That is also an example of simple harmonic oscillation. If you look at how electrons move in the atomic model, in our model of an atom, it's a simple harmonic oscillation. Our very existence is a vibration. Some physicists believe that everything that oscillates fades out of existence at a specific frequency. So if you could phase shift the existence of the right hand from the left, they could pass right through each other. But then one would exist when the other wasn't there, and vice versa. I don't even know if it's possible, but it's just to give an example that there are oscillations everywhere around us. Even our moods fluctuate. For some, it's more than for others. That's just how we're made differently. So let's now try to look at the model example of simple harmonic oscillation. And we can see that it becomes a second order differential equation soon. So imagine that you have a wall here. And in the wall, you have secured a spring. So that imagine it is a spring. And such a spring is characterized by something called the spring constant, K. It is a measure of how strong the spring is. If K is a big number, then it is a very strong spring. If K is a small number, then it is a very weak spring. At the end of the spring, we have attached the cart with the mass M, with a couple of wheels on, so that the cart can move frictionlessly back and forth on a surface. In reality, nothing is frictionless, but on the board it is. So we assume that there is no friction here. It moves completely frictionlessly back and forth. A physicist would say that this K is measured in the SI unit of newtons per meter. And that means for every meter you deform the spring, it yields a certain number of newtons. You can now imagine grabbing the cart, pulling it slightly to the side, and then letting go. And then the cart will rock back and forth like this, swinging, 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 swinging. And how quickly it oscillates back and forth is called the resonance frequency. And it turns out that it depends on how heavy the cart is and how strong the spring we have used is. And you can set up mathematics. It describes how the cart should behave if Newton is correct. And this leads to a second order differential equation. If we solve this differential equation, and we will do that in a moment, we get a prediction of where the cart is as a function of time. You can simply solve the differential equation, and the solution tells us where you can have the cart, depending on when I ask. And that is called a position function, because it's a function that tells which position the cart is at different times. Are you following this? To solve the problem, you need to know about Newton's second law. So if you've forgotten it, they'll review it. Newton's second law.
And Newton's second law states,
the simple version you learned in high school is called force equals mass times acceleration. And what does it say here? It says that if you have a force that is unbalanced, then it's only that force. It can also be the sum of force and GF. So if I have some force acting on an object with mass m, what would the object do? It will accelerate.
Where will it accelerate? In the same direction as the force.
So when the force is that way, the cart accelerates that way. When the force is that way, the cart accelerates that way. When the force is that way, it is not certain that the cart is moving that way yet. You can accelerate in that direction while moving in that direction. That's called braking. So that is Newton's second law. And if you write it as you learn in more advanced physics, you write it like this. Take the sum of all forces present and add them together as vectors.
That means you now take the sum of all the forces.
Then you get mass times acceleration. So what is it that he wrote? Those two little dots that were here. That means you have differentiated twice with respect to time. Because when you do a trick, it means you differentiate with respect to time.
And vector notation means that it is a vector. Because acceleration, what is it?
It is speed they deserve. Because when something accelerates, it is because it changes speed. So when you differentiate speed, you get acceleration. But what is velocity? It is the derivative of position. So if you take the position and differentiate it twice, you get acceleration. And now we will use this second law of Newton on that cart. That results in a second order differential equation appearing. And now we draw what is called a free body diagram. Right now it all sounds like we are in a physics seminar. And we are for a bit more. One draws a free body diagram. M is an M. Now I draw that mass M. And what does free body diagram mean? It means isolate the cart from the surroundings and draw all the forces acting on the cart. Draw them on the cart. It's a free body diagram. So I'm going to try that. And what forces act on it? Well, we could imagine that it's all happening in the gravitational field G. So there is a gravitational force downward on the cart, which is the size of M times G. We've learned that in physics class. And then there is a force from the ground upward on the wheels. Now I am only drawing on one wheel, but the force acts on both pairs of wheels, of course. There. That's called the normal force. I call it N for normal force. But the gravitational force downward and the normal force upward cancel each other out. So they are not important. I just drew them to show you that they are there. What's important are the forces in the direction of the movement. And since the cart intends to move in this direction, only forces in that direction are truly interesting. You should now imagine that
You measure where the car is located.
from the relaxed state of that spring. Because a spring can either be compressed, stretched, or it can be relaxed. And we measure the position of the cart from the relaxed spring position.
So imagine that.
We have our spring.
How should I draw that?
We are drawing our spring here. And then we say, here is the spring in its relaxed position. So I call it.
That's what I call x equals 0. That place there. That place.
And then I pull the cart to the right until it's out here where the cart is. So I've actually deformed the cart to X, some sort of spring deformation. Are you following? So I kind of take the cart and do this.
Total the x to arrive on that.
So is X positive or negative? It is positive because I count positive to the right. That's what this arrow here shows.
So I have pulled the cart to the right. X
It's
is greater
positive
than
to look
0.
at my drawing. It might be that X
Good evening.
is greater than 0 in my drawing.
That means the springs have been stretched. By how much?
X. And what does the spring do? We have started it when it responds to a force.
We call it the fourth force on the cart, which points the other way.
So now there's coming
Power on the cart. Because I have direct power, a force emerges.
on the cart that way. In English, this force is called a restoring force, meaning a force that seeks to restore balance. It wants to return to zero spring, where it is neither stretched nor compressed. And this force is called the spring force.
So a force comes that way, which is the fourth force.
Oh. Then I look at my drawing, and then I say, how strong is that spring force? Well, that spring force as experiments can show, is proportional to the spring deformation. The more I deform the springs, the greater the force becomes. This is called Hooke's law. Many of you have probably heard about it in Physics B at some point. And the force points to the left, but I calculate positively to the right because I have my
Coordinate oneself to point to the right here.
So that means the force is in the opposite direction of the direction I'm counting as positive. We need to consider that with what I'm writing now. Now I'm using Newton's second law. People usually just write N2 when they want to tell someone they're using Newton's second law. So what does Newton's second law say? It says, take the sum of all forces. And all the forces that interest us are those that lie in the direction of the x-axis. So we write that down here below. And then you draw an arrow. And what that means is to take the sum of all forces acting in the direction of the x-axis and count positives to the right. That's how it's supposed to be read. And what should they equal? According to Newton's second law, it should equal mass times acceleration. And we write it like this. And we drop the vector notation because we know the acceleration will occur in the horizontal plane, so we don't need to use vector calculations. We only look at the magnitude. We forget that it's vectors. So here stands Newton's second law. And then we take the sum of the forces. Which forces are there? Look at the drawing. Yes, there is only one force in the x-axis direction, and it's the red force, because the other two forces are not in the x-axis direction. So what is the only force here? Well, it's that one up there, minus kx. And why do I write a minus sign now? It's because the force points to the left, so it gets a minus. Are you following this? So here it is. That there. It is a second order differential equation.
Because what is x in that equation?
Well, x is actually the position as a function of time.
Where is the card? Like functions and what time it is.
And that means if I just divide this equation by em and move it to the other side, it says x prime of t plus ket divided by m multiply x by t. Should I buy you a beer?
And that's how you typically write that differential equation.
So this is an example of a second order linear equation.
And it is properly emulsified.
And then one might ask, what is the solution to that? That is the problem. What is the answer to that problem? Well, it is evidently some function x that if you differentiate it twice and insert it there, and take it untouched and insert there, and multiply by a constant, must always equal 0. And what kind of function can we think of that when you differentiate it and add it to itself multiplied by a constant, it always gives 0? What could that function be? You need to differentiate twice. Well, it could be sine, because differentiating sine gives cosine, and cosine differentiated gives negative sine. So you can see when you differentiate twice and add it with itself, you could get it to equal 0 if you choose sine. So we guess, and it's obviously a pretty qualified guess, because we know that if you take a card and pull it and let go, it behaves like this. And if someone stands here with a spray can, while a man runs past with a piece of paper infinitely long, you draw a sine wave. So we guess that is sine or cosine. In this case, we choose sine, but one could also have chosen cosine. So we guess that the solution looks like this. We guess that x as a function of t is equal to some amplitude of.
Amplitude means the magnitude of fluctuations.
Sine.
To some angular velocity times the time.
That's our guess. That's called angular velocity, and physicists measure it in radians per second. So if that is 2, it means that sine cycles through 2 radians per second. And when you multiply 2 radians per second by a number of seconds, you get a number of radians as the resulting angle. Then you take the sine of this angle and multiply by the amplitude. And what do you get? The position of the car at that moment. If this is indeed a valid answer, and we will now see that it is, let's now try to see if we can make this answer work by substituting to see what is needed. We insert it into the equation. I will call the equation star. So this is my star equation. And now I will substitute into it. To substitute, I need to differentiate it first once and then once more so I can insert x there.
So I'll just find x dot.
Some people call it x dot.
I've watched too many English videos, so I'm going to call it x dot. So when I differentiate once with respect to time, what do I get? A is a constant, and constants that are multiplied remain when we differentiate. Sinus differentiated becomes cosine. So I need to work with cosine for the same argument as before, which is called omega t. But this is also a function. So this is actually a composite function. So I need to remember to differentiate the inner function, and that gives omega because I have to differentiate with respect to time. That gives omega. Is that clear? So when I differentiate a sine omega t, I get a omega cosine omega t. Then I need to differentiate once more. So I find x double dot or x double prime. And then we think a remains for the constant it is multiplied by. Omega stays for the constant it is multiplied by. So I can just copy paste them. Differentiating cosine gives negative sine. And omega t should be differentiated again, and that gives omega again. So when I multiply by it, I get omega squared. Well, yes, just shout if you're not following. So that differentiated gives that. Now I'll take that and think that it should go into x's place, and that should go into x's place, and then I'll see if I can make it equal 0. If I can do that, then the guess works. But just notice something. Can you see that x of t looks quite a lot like x prime of t? There is an a, and there's a sine. There is an a, and there's a sine. So what's the difference? Minus omega squared. So here it really just says minus omega squared x of t. Can you see it? Because if you took this x of t here and inserted it down there in the place of x of t, you would get exactly that.
So that means that what is written here, I can put that in the x double tag slot. Then it says minus omega squared x of t, and then it says plus k divided by m. X is t,
And it must equal 0. And it must equal 0 for any value of t. You can see that x and t appear both here and there. So we call it a common factor, which I must place outside the parentheses. So I get x of t times parenthesis k divided by m minus omega squared. Can you see it? Because if I multiply this with that, I get this term. And if I multiply this with that, I get that term. So it must be correct, and it must equal 0. And now we can use a clever concept called the 0 rule. Because the 0 rule states that if this product of two factors must equal 0, then either one factor must always be 0, as it must hold for every value in time, or the other factor must be 0, always. Can we rule out one of the two? Yes, it can. It can't always be x of t that's 0, because then the cart wouldn't move. We assume that if we pull the cart to the side and let it go, it will move. So if this factor was always 0, we would get the world's most boring solution to the differential equation, namely the 0 solution, where the cart just stays still. Is it a solution? Yes. Is Newton's second law upheld? Yes, because there are no forces, there is no acceleration. Thus, Newton is correct. Forces equal mass times acceleration. But you can see that it's the trivial 0 solution. That's not what we're after. So if this product is to give 0, and it's not this one that is always 0, then it has to be that one that is always 0.
So that means my guess only works if this is 0.
But if this is supposed to be 0, what then? Then we can conclude that k over m minus omega squared must equal 0. Who is it that I don't know here? Is it Madsen from the cart? No, we have to assume that we have weighed the cart before conducting the experiment. Is it the spring constant we don't know? No, we purchased the spring ourselves from Lechefors, who sells springs. So, we know what kind of spring it is and what kind of cart it is. What we don't know is the angular velocity it oscillates with. That's what we don't know. So we isolate omega. So, we just move omega squared to the other side of the equal sign and get omega squared equals k over m. And then we need to find omega. And we simply take the positive square root on both sides. There are indeed two solutions to that equation, but they are equally good. So why not take the positive one? So I say that omega is the positive square root of k over m. Here stands something important. That's probably the last
Important?
equation in physics right there. Because it shows how quickly does something that swings actually swing? And the answer is, it depends on how stiff it is and how much it weighs. Take a metal rod, it's really strong. You pull it to the side and let it go. It is very stiff compared to how heavy it is. If we take a long floppy rod, there isn't much mass. Then it just flops around. Can you see it?
So here's what it actually takes to make it
What
rain.
frequency does a guitar string vibrate at? It's pretty wild, actually.
It gives you
So that
goosebumps.
means this A times sine of omega t is the solution to the differential equation, but only if omega is correct. Only if you take the right sign that oscillates with the correct angular velocity does it work. Namely, the one that corresponds to the system wanting to oscillate at precisely that angular velocity. There's something called natural frequency. And what is that? Well, we know there's a relationship between oscillation period and angular velocity. So if you remember from physics, you probably learned once that there is something called oscillation time. It is the time it takes to complete an oscillation, essentially. It is also called the period. That is 2 pi divided by the angular velocity. So if you ask, how long does it take to make a full oscillation? What is the answer then? It's how much a full oscillation is in radians divided by how quickly you go through angles. Can you see it? This is how far you need to travel. You need to travel 2 pi radians. This is how quickly you travel through angles, as that measures the radians per second. So the oscillation period becomes 2 pi radians divided by omega radians per second. That means if I want to have the frequency is the reciprocal of the oscillation period. Because if it takes, let's say, 1/10 of a second to make one oscillation, then this number is 1/10. If it takes 1/10 of a second to make one oscillation, how many oscillations can I then make in a whole second? Okay, and the reciprocal is 1/10, which is 10. Therefore, frequency is the reciprocal of the period. So this is the same as flipping this fraction upside down. Then it says omega divided by 2 pi. But I have already found omega. It's written up there.
So now I have a formula for
The natural frequency is a harmonic oscillation. It is omega, which was the square root of k over m.
I want to be with 2 girls. And you usually write it like this, 1 over 2 girls.
Danish subtitles by Nikolai Winther. And it comes out in something called hertz, if you're a physicist, where it is a number of oscillations per second, so it's measured in seconds to the power of -1, or reciprocal seconds. That means the day you know how heavy the card is, and you know which spring it is attached to, you can calculate how long it takes to make an oscillation. That was one oscillation. That was another oscillation. And it's just about putting it in that form. And how do we figure that out? We solved a second order differential equation. And what is the second order differential equation? It's really just Newton's second law, because Newton's second law is a second order differential equation. Now, I hope I haven't completely scared you away with something. I hope that I made it much easier. Suddenly it turned to physics, but that was my introduction to why we should learn about second order differential equations. It's because in the nature around us, there are many phenomena that vary cyclically. Also in chemistry, fortunately. Let's take a 10-minute break and then we'll see if anyone wants to ask questions afterwards.
Okay, we got to take a break.
Oh, good.
We will briefly go through the story where you don't need to take notes simultaneously. The title is Second Order Linear Differential Equations. So we're going to learn a bit about that. And then we ask ourselves, where do we encounter this? A classic example is when things oscillate. So let's take a look at a simple harmonic oscillation. What is it? Well, that's what it's called when you have an object with some mass that oscillates back and forth around an equilibrium position. Here, the equilibrium position is where the spring is neither stretched nor compressed. It's where it naturally wants to be. And right at that point, we call it x0. That's here. And the spring is in its relaxed position. Then I stretch the spring. The spring is still attached here in the wall. It's also attached over here. but now it's stretched out, so the spring goes all the way out here and attaches to the cart. As you can see, the spring is stretched by a distance x. And then we use Newton's second law, which states that force equals mass times acceleration. Or the sum of the forces equals mass times acceleration, if that makes sense.
Cost.
So we draw this mass isolated from the surroundings and ask what forces are acting on it. There is a gravitational force downward on the cart and a normal force from the surface upward on the cart. If this weren't the case, it would just crash through the floor. And then there is a force from the spring on the cart. When the cart has stretched the spring, the force points to the left. This is why I have drawn a red force to the left, which I call the spring force. So that spring force causes the cart to accelerate. When I pull the cart to the side and let go, the cart will accelerate because the spring pulls it. But once the cart reaches the middle, where the spring is in its unstretched and uncompressed position, the cart will no longer accelerate. Now it has maximum speed in the cart, and it has built up speed until now. But there is no longer any force on it, just in that lucky second when it's in the middle. But as soon as it moves past the middle, it compresses the spring.
Yeah.
And now there is a force in that direction on it, so now it breaks. That means it accelerates in that direction. So when I pull the cart to the right and release it, it accelerates in that direction. Until it reaches the middle, it doesn't accelerate. And when it passes the middle, it accelerates in the opposite direction and slows down. This continues in this manner, and that movement is a simple harmonic oscillation. And then we use the fact that the force from a spring is the spring constant times how much the spring is deformed. The deformation of the spring is measured in meters, and that is measured in newtons per meter. So if you take some newtons per meter and multiply by some meters, you get some newtons. So that is the force measured in. And when we then write down Newton's second law, we see that there is only one force in the horizontal plane, and it's the red spring force, which points to the left when the cart is to the right, and points to the right when the cart is to the left of the center. So that red force is constantly changing magnitude and direction during the oscillation process. And while the spring force changes, Newton's second law must be upheld. That's what we've written here. Mass times acceleration is always equal to the force that causes that acceleration. Are you following? Then take that term and move it to the other side of the equation, so it becomes m times x double dot plus k times x equals 0. Then go through the equation with m. So there is no m in front here. The equation then looks like this, and it's called the equation of motion for a simple harmonic oscillation. And that is what it really is, according to Newton's second law. But from a mathematician's perspective, it is also a second-order differential equation. The task is to find a function x that, when differentiated twice with respect to time, and then added to itself multiplied by a constant, will always equal 0. And we can certainly think of a function that could satisfy it. Namely, our guess is a time sign of some number times t. And if you remember when you learned about sine, you may recall that if you multiply it by a large number, it oscillates quickly. Multiplying by a number here that is small makes it oscillate slowly. So that number omega indicates how quickly the oscillation occurs. And what we end up showing is that how fast the oscillation happens depends on which spring we buy and how heavy the cart is. And that's what our intuition would have predicted. So to solve this differential equation, I guess that solution. And to see if it's a good guess, I insert it and see if I can make it work. So I differentiate it twice and get this. And recognize that what is there resembles what was x. So therefore it says minus omega squared x here. So I insert negative omega squared times x into the position specified here. Plus k over m times x, it says there, and it should equal 0. Then I see that I can factor x of t out of the parentheses here and get that something multiplied by something else must equal 0. So I use the 0 rule and say that two things multiplied together can only equal 0 if at least one of them is 0. And it's not this one that is 0 all the time. It can indeed be 0 sometimes, but it can't be 0 all the time because remember what x of t was. It was the motion. So if x of t was the motion and it was 0, or if x of t was 0, it would mean that the cart was stationary right in the middle and never moved. So the only way for this equation to equal 0 for any value of t is for what's inside the parentheses to be 0. And that's what I've written there. This sets the exact requirement for what omega becomes. Omega becomes the square root of k over m. Which omega? the omega that tells how fast the sinusoidal oscillation occurs. And it makes good physical sense that it is determined by the spring stiffness and how heavy the card is. And the last thing I do here is find the frequency, which is the number of oscillations per second. It ties together nicely with omega. Then I get that formula. Does that help? Okay. You don't need to explain this in an oral exam. This is physics. This was just to show you what you can use it for. You'll encounter this if you're an engineering student when you study dynamics. So this will come up again. That's how you get to enjoy it again. Or perhaps despise it once more, depending on how you feel. Now back to the headline. Second order linear differential equations. Now comes the math part. Table 3. Every time I speak, I've noticed that the English translation becomes really weird. It hears bits and then starts rambling. All sorts of strange English, supposedly said by someone. It just makes something up.
You're just sitting out there having a nice chat.
So if you do not want to quote us as saying something we never said, watch out if I chatter too much.
Yes.
No, I have made them separately. English on another channel. All the English ones are not on Absalon's site, but on my own. I can send you the link afterwards if you want. What is a second order linear differential equation? If it is a second order linear homogeneous differential equation, it looks like this. Some function a of x times y differentiated twice, plus some other new function b of x. Multiplier differentiated once, and plus some function c of x times y, not differentiated at all, must be equal to 0. If a differential equation can be written in that form, it is called a second order linear differential equation with variable coefficients and homogeneous. That's a lot of words to remember. Our mathematics course does not give enough ECTS credits for us to really learn how to handle one. So we will only say a little about it. What we do need to learn about is when a, b, and c are not functions, but just constants. And then it's a bit easier to handle. But what we can say about this differential is that it has a wonderful property. And this wonderful property states,
When you say the first thing, I'll write it down.
if you have two functions that
That's
run
how it is. And you call one of them.
y1 and the other y2. So you have two functions that are solutions to them. Then a similar a combination of the two will also be a solution. That was a claim. And the assertion, that usually works well in mathematics. I will just write that down as a sentence.
And the sentence sounds if y1 at x. Year 2 during x
are 2. The solutions are linearly independent. And now we need what we learned in linear algebra. Because when something is linearly independent, it simply means that one y cannot be written as the other times a constant. If they cannot. So if one solution is called x squared and the other is 2x squared, are they linearly independent? No, they are not. Because 2x squared can clearly be written as a constant times x squared. Specifically the constant 2. But look at this function. E to the power of 3x and e to the power of 4x. Are they linearly independent? Yes. It doesn't matter which constant I multiply by here. No matter the constant, it can never become that, because it has changed the exponent. So they are linearly independent. And what we are saying now is that if you have two linearly independent solutions to that differential equation, if they are two linearly independent solutions to the star equation, which is what I call the star equation. Then any linear combination of them will also be a solution as well. So, any so? Then there is one. No, one should approach it with goodwill. One. Line A combination. Of y1 and y2. Race conservation lighting.
And what does that mean? It means that this will then
C1, where it is a constant C1 times y1,
10
plus C2 times I2 of x. It will also provide a solution. So this y is also a function of x. It's just that you don't always want to write of x. But what you're looking for here, let me make that absolutely clear for you. You're looking for a function y, specifically y of x, something that depends on x, which when differentiated twice times that function, plus differentiated once times that function, plus undifferentiated times that function, should equal 0 for any value of x. That's what you're looking for. And what the sentence states is that if you have first found one solution that works, meaning it gives 0, when you insert it, and you have also found another solution that works, meaning it equals 0 when you insert it, then any combination that looks like this from the two solutions will also provide a function that works, meaning it equals 0 when you insert it. And this can be proven. And I will just show it to you, because it is not so difficult to prove.
And you might be asked about that in the oral exam. So let's just prove it.
So here comes the proof. And you need to be completely sure that you have understood what I'm going to prove, because I have seen quite a few students come in and start on this, and you can tell they don't really know what they are saying in that sentence. So maybe I should explain it once more, very calmly. Here is a differential equation. The goal is to find a function that, when placed in y's position here and there, makes it equal 0. If you can find such a function, it is called a solution. So far, so good. If you have two functions, both of which solve them, and one is called y1, and the other is called y2, then I claim that if you combine the two by multiplying one with a constant, and the other with a different constant, and then add them together, you get what we call a linear combination. And I claim that no matter which constants you use, it will also solve. So any linear combination also solves the differential equation, if y1 and y2 do. So you can actually think of y1 and y2 as two linearly independent vectors, and the space they span forms the solution space. I don't know if you remember, but there was vector calculus. If this is one vector and that's another vector and they are linearly independent, as these two are, since they are not parallel, what do they span? The entire plane. So if you have one solution y1 and another solution y2, what do these two solutions span? The entire solution space. You just take one constant and scale one solution with it, and another constant and scale the other solution with it, then add them together, and you get all the solutions that exist. We are not proving that. We are just proving that it is a solution. We are not proving that it is the only one that exists, because that is a bit harder to prove. Yes, it is a complete solution. It's not just a solution, it is also complete and there are no others, but we are not proving that. And it's a bit difficult to prove, but we will prove that it is a solution. This is somewhat like saying that if this is one and this is the other, when you multiply one vector as a longer or shorter, and multiply the other vector by a number, then you can make it longer or shorter. And when you add the two vectors together, you get that one. And you can cover the entire plane depending on how you scale the two vectors. So we say they span the entire plane. Similarly, the two solutions span. Hello?
It's called the solution space.
Is that something you think? And let's try to prove it. There's a bit of writing involved, but there's nothing conceptually difficult in the proof at all. I don't think you'll find it difficult either when you've seen it. So what do we know? We start with what we know when proving something. You often begin with what we know. We know that 1 of x is a solution. And then there might be a sharp student who asks, how do we know that? That's what I've assumed. See, it says if. If y1 is a solution, I have written. So it is kind of an assumption in the statement. So now I say that we know that y1 is a solution, so it follows. So what applies? If it is a solution, then what I am writing now holds true. So it gives 0 when you substitute it, otherwise it wouldn't be a solution. Therefore, that function times y1 plus that function times y1 plus that function times y1 will certainly give 0. So it is a solution. And we know that y1 is a solution because we assumed it in the hypothesis. So we know that it holds that a of x times y1 plus b of x times y1 plus c of x times y1. This we know equals 0. So that's what applies. Do we know more than that? Yes, y2 is also a solution, so we also know that the following holds true. A of x times y2 double prime plus b of ax times y2 prime plus c of ax times y2. We also know that this equals 0. So we know that both this and that apply. Are you with me on that? And those C1 and C2 I have written here. C1 and C2. They are just some arbitrary real constants. So we can write it like that. Okay, let's see if this is a solution. Let's now test in the proof if there actually is a solution for this. How do you do that? Well, you simply substitute it in and see if it results in 0. If it gives 0 when you substitute it, then it is a solution, and then it is proven. So we now put this into the y double prime position, the y prime position, and the y position. But before we can insert it into the y double prime position, we need to differentiate it twice. That is this y. And before we can put it into the y prime position, we need to differentiate it once. And when we insert it there, we mustn't alter it. So it should just be copy-pasted directly. Are you following? So we just insert and test it. To see if the claim is true, so we insert this y equal to c1 times y1 plus c2 times y2. We insert that into the starred equation. And to do that, we need to differentiate it twice before substituting it there, and once before substituting it there. So let's first find y prime. And then you will see that it involves more writing than it is difficult to prove. Because how do you differentiate a constant multiplied by a function? Well, the constant remains, and the function is differentiated. So it says c1y1 prime. Then we take that one. It gives c2.
I2 mark. So now we have found the y mark.
So let's find the y double mark. That gives c1y1 double prime plus c2y2 double prime. Because again, I just need to let c1 and c2 stay and differentiate once more. So now I can take all of this and slot it into that space. And I can take all of this and slot it into that space. And I can take all of that and slot it into that space to see if it equals 0. And it does, but let's just do it. So first we get a of x times parenthesis. And now I could really have used my chalkboard because I'm running out of space. So I have to reduce the font size a bit. Now I've substituted y prime, then I get to this plus brx times parentheses. Let's get this one up. C, 1y1 prime plus c2. I2 prime, like that, that was it. And finally, I need to have plus c and x.
Multiply c1 and y1, then add c.
And what does that yield? So you just inserted them?
them?
It equals 0 yet. So I don't write 0 immediately, because that would make me finish too soon, you could say. I don't know if it equals 0 until I've looked at it. But what you can see now is that if I take everything involving C1, what do I have then? I have C1 there, I have C1 there, and I have C1 there. So I just put C1 outside a parenthesis. So all of that can be written as what I'm writing now. What do I have with C1?
Yes, huh?
A x y and a double prime. A x y and a double prime. What else do I have? I have B ax plus B ax times via mark from here and over here. I have plus C ax.
Gang Y1, were you in on that?
There. I place C, 1 outside the parentheses. So I've multiplied this by that, it's here. And this by that, it's here. And this by that, it's here.
Then I'll put C2 in parentheses.
And what is there then? Well, something came from here. So there is A of x. A of x.
Each here.
Plus B is x times y2 prime. And plus C is x times y2. So I can simply rewrite all of that to that by just multiplying and factoring out. And now we are done. Because what do we know? Well, we know that this is an oil. How do we know that? Well, because y1 was a solution. And if y1 is a solution, then y1 inserted there, and that will give 0. And that's exactly what's stated here in the parentheses. It's precisely y1 plugged into the differential
Thank
equation.
you.
Written down here, I know it gives 0. And what do we know about this factor? Well, it also equals 0.
And it is
And a
in
constant
2.
times 0 plus a constant times 0 still equals 0. So now we will show that it results in 0 when you substitute that in. Well, then it's also a solution. So I have proven that any linear combination of two solutions results in a new solution. And what can be proven is that there are no others. So the only solutions that exist for this differential equation are those obtained by linearly combining two solutions. But the two solutions must be linearly independent. It must not be the same vector said twice. And this might seem a bit heavy, but it's actually pretty cool to know that if I've just found two solutions, then I'm basically done. I have the complete solution. So I will now show you, before we take the next break, how to solve a differential equation like this one. If this, and this
Only
are simply
constants, not functions. It just would have shown that it applies if they are functions. Okay.
But then
we don't deeply engage with
so
what we learn.
we will only need to
use this theory in the case where A is x, B is x, and C is x are not functions at all, but are constants. So that's the next board. Is there anyone who needs a picture in here before I wipe off? What do you make of it? I see a lot of sleepiness in the eyes when I look out. It's almost like a mirror because I'm quite tired too. We've been doing mathematical modeling, so we're getting a bit tired too. Okay. Okay, so the title is second order linear differential equations with constant coefficients now.
So this headline gets a bit longer, eh?
With constants coefficients. This means that such a bandit looks like this. Some constant a times y prime plus some constant b times here. Plus some constant c times y prime must equal 0. This differential also appears in many places in nature. And we have just seen an example, namely the harmonic oscillator. So it's cool to be able to solve it.
And now let's see if we can guess how to solve it.
So here comes a guess, and you need to hear where the guess comes from. I haven't just pulled it out of thin air. we are looking for a function y of x, such that if you differentiate it twice and multiply by a, differentiate it once and multiply by b, and do not differentiate it and multiply by c, then add it all together, it should equal 0. And it should not just equal 0 for a specific x value, but for all x values. What kind of function could it be? Where you differentiate it twice, once, and not at all, then add them up, and it gives 0. It doesn't have to be something with e to the power of x, because e to the power of x, differentiated, just gives itself. So it can't just be e to the x. It almost has to be e raised to something clever times x. Do you follow what I mean? Because if k were -1, what does e to the power of -x give? Well, it gives e to the power of -x times -1, because you had to multiply with the other differential quotient. So you can see that you can get them to cancel each other out and equal 0 if you choose this as the guess. Can you envision that? So my guess is that my function y is called e to the power of kx. And that k, I actually don't usually call it k, so maybe I should call it what I usually do. So you can see it in other videos too. I usually call it lambda, but it doesn't matter. It's just some constant. I is a raised to the power of lambda times x, where lambda is some constant number that can be chosen freely. This is my kit, and now you will see that the guess works. So we substitute in the star equation, and now it is this one called the star equation, because we have reached the next chapter. So we substitute into the star to see what should apply. So now you need to help me. If y is e to the power of lambda x, what does y prime become? It gives e to the lambda x, if you remember, to multiply by lambda, because it is a composite function. Notice, is equal to e to the lambda x, multiplied by lambda x, differentiated, because it is an inner function. And it also needs to be differentiated, which gives lambda. So that means when I find y prime, I get lambda e to the power of lambda x.
That also sounds really nice when you say it. Listen.
Lambda times lambda x.
Yes. Then you feel uplifted once you have said that.
Okay, I can feel I'm a bit tired too. Something about saying relationship with the dough, you know. Then it differentiates once more, because I needed both y prime and y prime to substitute up here. I want to differentiate it once more. It again gives lambda e to the power of lambda x. But I have to remember to multiply by lambda one more time, because it changes the function again. Differentiating gives lambda, so it becomes squared. And now something happens that is nothing short of magical. When I put that there, in that place, and should I not display it? And then I put that in that spot, and I'll put that right there in that spot. Then something magical happens, because it's easy to see here what must hold true, as it equals 0. And what needs to happen is that one should be able to solve a second equation. And then you will need beloved mathematics after you've learned this. And then you think, finally I got to use the second derivative line. It might be that I needed it for something I don't understand, but at least I need the second equation. So let's try to insert it. So it shows when we insert, it says lambda squared e in lambda x, but it needs to be multiplied by a, you see? So I'll just write an a in front here. Plus b.
Plus b times y mark, but y mark was lambda a in lambda x.
And then plus c times y, so plus c times y, but y was e to the power of lambda x. And we would like that to equal 0, if possible. So now you can see that the e lambda, which is not present here and there, is called a common factor, and you must take it outside of a parenthesis. So I get rewritten it to this, e raised to lambda x times parentheses. What do I have left? A times lambda squared. Plus b times lambda.
Or plus c.
And it has to equal 0. So we use the 0 rule. If this product is to be 0, then either that must be 0 for any value of x, or the inside must be 0 for any value of x. And note that this cannot be 0, because e raised to lambda x can never be 0, as it is an exponential function, and it lies entirely in the upper half plane of the coordinate system when you draw such an exponential function. This is what it does. So e to the power of lambda x cannot be 0.
So the only possibility for this to ever become 0 is if the inside part here, if it equals 0, and it can indeed equal 0, because what is it then? A quadratic equation in lambda. Have you ever seen something like x squared plus bx plus c equals 0? Yes, that's a quadratic equation in x. But this is a quadratic equation in lambda, and it's called the characteristic equation
When
for it.
considering such a differential equation with constant coefficients.
So we call it the characteristic equation. So this, a lambda squared plus b lambda plus c equals 0, is called characteristic equation, because it tells you the character or type of your differential equation It's called the characteristic equation for the star. That is, for this differential equation here. And now there are 3 possibilities, and you know them. Because when you have a second degree equation, it can have a discriminant that is greater than 0. Then it has 2 real solutions. It can also have a discriminant that is 0. Then it has 1 real solution. It may also have a discriminant that is negative. Then it has 2 complex conjugate solutions. This is how you should use complex numbers as well. It's going to be great. So here come 3 cases. This means that such a differential equation always falls into one of 3 cases. One is called overdamped, the other is called underdamped, and the last one is called critically damped. But the interpretation will come later. But they correspond to 3 cases, namely those determined by the discriminant of the characteristic equation. The first case is that the discriminant is greater than 0. If that equation up there has a discriminant, it's just a regular second degree equation. So it could be written as 2x squared plus 7x minus 5 equals 0. Now, it's not called x, it's called lambda. These are the lamb owners we are finding. Okay, and when we have found lambda, where do we put the lambdas? There. And what do we get then? Solutions. To what? The differential equation. See, when you solve that equation, if it turns out that lambda equals 2 works, then you can just put 2 in there. Then e to the power of 2x will be a solution. If you find that this auxiliary equation is solved by minus 5, you simply set lambda to minus 5 there. Then it says e to the power of minus 5x. That is also a solution. Are the 2 components independent? Yes. Then you simply combine them and you have the complete solution. With what I demonstrated on the previous board, you make a linear combination of the 2. So if the discriminant is greater than 0, what do we know then? We know that there are a lambda 1 and a lambda 2. There are 2 different lambdas that solve that equation. Thus, lambda 1 and 2 are solutions to, what should we call an equation here? Should we call an equation square?
No, there are solutions for the quadrilateral connection.
Oh. What do we know then? Well, then we know that this will be a solution. E to the power of lambda 1x, that will be a solution. So I1 equals that, which is a solution.
Oh, we take 2.
Equal to e raised to this, lambda 2, x, will also be a solution. It will be solutions. And then, because these are solutions, what do we know? Then this will be the complete solution. Some constant c, 1 times this one, plus some constant c2. The idea changes. Then this is the solution. But it is only a solution if the discriminant is greater than 0. Is everything okay?
I'll give an example showing how it's done in practice.
Case 2.
What if the discriminant is 0? If the discriminant is equal to 0, so it means I only have 1 bureau desk lamp.
Now I'm speechless.
One solution for the attack line, and there's only one. So now I don't have two lambdas. Now I have only one lambda. So lambda is a solution. By the way, do you remember how to solve a quadratic equation when the discriminant is 0? You solve it like this, minus b over 2a. Here's how we find countries. If the discriminant is 0. Up here, how do you find lambda 1 and 2? You do it like this. I should also write it down for you. It's the solution formula for a quadratic equation. You might have forgotten it. It's negative b plus or minus the square root of d. The whole is divided by 2 times a. That's how you find the two solutions for a quadratic equation if the discriminant is positive. But what do you do now if there's only one solution? Then you have a bit of a challenge, because now you only have one vector. And one vector can't span the entire two-dimensional space. In the same way, one solution can't span the whole solution space of this second-order differential equation. So, you use adjustments.
What do we know? We know that this is a solution.
The lambda we do find, if you insert it in lambda's place, you get a solution. Are you following that? But you need two similar independent ones to write the complete solution. And it can be proven, and I don't know if I'll have time to prove it, but it can be proven that you can find another solution, y2, by just taking x and multiplying by e to the power of lambda, x. It becomes similar, independent from the first one. So now you just combine the two in a linear combination, and then you have the complete solution. So the complete solution here, when the discriminant is 0, becomes C1.
E lambda x
Plus C.
X times e to the power of lambda x.
Where those constants C1 and C2, they are arbitrarily real. Now I can see there's a row of you falling asleep. So let's take a 10-minute break before I cover the last case, where the discriminant is negative. Then I'll show you some examples, and we'll spend the rest of the day practicing outside, so you really get to work on it. Because this story is something you can't remember unless you've stood and told it yourself. So let's take a 10-minute break. So we took a break, and we still need to discuss the last possibility. There are three cases for the characteristic equation. The discriminant can be greater than 0. It can be equal to 0, but it can also be less than 0. And now I wish I had a bit more board space so the camera could see, but unfortunately, I have to leave some things out.
So if I just have to step out here.
So the last possibility is that the discriminant is negative. So that is option 3. If d is less than 0, and we know that if d is less than 0, you get 2 lambdas, and there will be 2 complex numbers. And now I write them like this: alpha plus or minus I times beta. And what that means will probably become clearer when examples are given. But it could say 2 plus or minus 3i, for example. It turns out that when you have a discriminant that is negative but still real, you always get 2 complex solutions that are conjugates of each other. And can you remember that conjugate means changing the sign of the imaginary part? So alpha plus I beta is 1 lambda, and the other lambda is alpha minus I beta. And that is the conjugate number corresponding to alpha plus I beta. Well, and if you are in that situation, the solution looks like this. It is a complete solution. It becomes Euler's number raised to the power of alpha times x.
Multiply parentheses by a constant C1.
Times,
Let's see if I can remember it. Cosine.
until beta 10.
Plus C.
Sine of beta x.
So here's what the solution looks like if you're in the situation where it needs to be negative. And just to make sure I'm not telling you lies, let me check if I remember it correctly, because
For some reason, it's always hard to recall.
The course is also correct.
It's correct. I remembered it right. You can prove it. It's always easier for me to prove it than just to blurt it out, because the proof reveals itself if you can remember it. So here is the solution. If you have two complex conjugate solutions to the characteristic line. And now let me show you some examples of how to specifically solve these second-order linear differential equations with constant coefficients. Because then you can see it's not that difficult. If you can just solve a second-degree polynomial, then you can solve it. Is there anyone who needs a picture before we need to go out?
Yeah, you can watch the video, right?
It might be nice to have a formal gathering somewhere.
I'll just move a bit so I'm not included here.
All right. Table 5. Let's look at some examples. And afterward, we'll go out and practice the proofs. If we have time, we'll work on a couple of problems. And if not, I'll write some tasks for you when we are finished. But let's try and see how it's done in practice. And that's the thing with mathematics. When I say let's see how to do it in practice, it's often just some new math examples that have nothing to do with reality. But that's because, you see, as soon as it relates to reality, the complexity increases. The best examples to start with are actually those that are pure math examples. Even though they don't involve any physical understanding, you just learn to use the method. So here comes example 1. Let's say he is from a count called ymark. Plus y. E prime plus e prime minus 6 times e equals 0. What have I created there? It's a differential equation. It is second order because it is differentiated at most twice. It has constant coefficients because there are hidden 1 and 1 and a negative 6 as coefficients. It is homogeneous because there is 0 on the right side, and it is linear because it follows this nice solution structure. Linear combinations of solutions yield solutions once more. That is how linear works. How do you solve it? You write down the corresponding characteristic equation, which is an auxiliary equation, in lambda, and solve it. The first thing I do is ask, what is A, what is B, and what is C? Well, A is here, it is 1. B is here, it is 1. And C is here, it is negative 6. So my characteristic equation looks like this. Lambda squared. And it should really say 1 times lambda squared, but I don't want to write that out. Plus 1 times lambda, which is just lambda, minus 6 equals 0.
Here is the characteristic equation for the differential equation.
And it was the one I showed earlier that appeared. And then I just solve it. So we find the discriminant. And the discriminant is b squared minus 4a.
Now we're back to B number math once again, as we've learned.
And what does that give us? Well, b is 1. So it will be 1 squared minus 4 times 1, because a is 1. And times c, but c is negative 6. And now we can see that I've been kind to myself, because minus times minus is plus. So here it is, 24, because 4 times 6 is 24. And adding 1 more, it equals 25, which is a square number. So I make sure it gives nice numbers. And then some might say, how can you predict that? It's just because I've used the example before. So you can pretend you know it by heart. But I could remember that the other gradient is called x squared plus x minus 6.
Had a discriminant called 25.
I've used that a few times as an example.
So I just used that again here. So now I know that the discriminant is greater than 0. And that means there are 2 solutions. So we know there are 2 eigenvalues. We can find them. So let's find them. How do the lambdas turn out? Now I can write them at once. Lambda 1 and 2. It's a shorthand way to write it. Here are both lambda 1 and 2 at once. It is minus b plus or minus the square root of d, all divided by 2 times a. That's how you solve an equation. And then I just insert the numbers. What was b? B was 1, so it's minus 1 plus or minus the square root of d, which is the square root of 25, then divided by 2 times a, but a is also 1, so that gives 2. If I use the plus, I get negative 1 plus 5. That is 4, divided by 2, that is 2. And if I use the minus, and now I'm curious how chat can pay, I plan to translate it when I'm playing around and say the minus instead of the minus. So I get minus 1 minus 5, that's minus 6 divided by 2 is minus 3. So there are 2 lambdas, which are 2 and negative 3. So I'm done. Now I can just write down the solution. I have the solution to the differential equation. It is all linear combinations of 2 solutions, namely e to the power of 2x and e to the power of minus 3x. So it's c1 e to the power of 2x
Plus C2.
e to the power of negative 3x, where c1 and c2
Can be an arbitrary chosen number.
Here is the complete solution. And then there might be someone sitting and thinking, well, what are those C1 and C2? Well, they are constants that you can sometimes determine, and other times you cannot. What does it take for me to find constants?
2 initial conditions are needed.
For example, if you know what y is at a specific point in time, and you know what y prime is at a certain point, then you can find the constants. But if you don't know that, then you can only write down the complete solution. So what you have here is a whole family of solutions, namely a solution for each chosen pair of C1 and C2. So if it's a physics problem, you often know some conditions that allow you to find C1 and C2, and then you get an exact solution. You can use a graph to see how the system behaves. But here in mathematics, we typically don't go further than here to C1. That's just it. It's trivial to find the constants. It's just algebra. Are you in on that? Example 2. And now I would like to think of an example where I know the discriminant is 0. I can't remember one. So I'll show you how I figure it out. If you write a structure that looks like this in mathematics, then you definitely get a descriptor that is 0. Because when you calculate this, it becomes a different equation. And the only solution for it is that x is 2. Can you see that? And if x is 2, then it says 2 minus 2, which is 0, and 0 squared.
That says it all.
And the only number that...
So there is only one.
A solution for this line is x squared. Are you with me? Are you with me? And if I just use the square of a 2-term expression to calculate this part, it gives the square of the first term plus the square of the second term minus the double product. Can you see that? X squared is the square of the first term. 4 is the square of the second term. The double product gives 4x, and there should be a minus in front because there's a minus. So this is the same as that. So now I know that this attack line has a discriminant of 0 because there is only one solution, and it is 2. And we can just try. What is 2 squared? 4 minus 4 times 2, that is minus 8. 4 minus 8, that is minus 4. Plus 4, that is 0. It checks out. So now I just create a differentiation line that looks like this. Second derivative, minus 4 times e prime plus 4 times y. And then I know in advance that this differential equation has a characteristic equation with a discriminant of 0. So if I'd been allowed to do this secretly, I could have pretended that I just invented a wonderful example that gave a discriminant of 0. But I'm so kind that I reveal all my tricks. I had to do that because I didn't really have a place where I could sneak around without you noticing. So here is the next example. And then we'll just remove the way I found it. How do we solve that second order linear differential equation with constant coefficients? We write down the corresponding characteristic equation, and the characteristic equation becomes lambda squared minus 4 lambda plus 4 equals 0. So now I'll just imprint this in my memory so I can remember it for the next class. Then I can act like I can invent one where it has to be 0. It's also a bit harder to keep it all in my head when the camera is rolling. I can reveal. Because normally I can just stand and think about what it should be, how it should work, but it's harder when the camera is rolling. Okay, so now we need to solve this second equation in lambda. So let's do that. What needs to be considered? B minus 4 times A times C. That means minus 4 squared. That's B. B is here. It's negative 4. Then minus 4 times A. But A is 1 because there's a hidden one there. And then times C, which is 4. And now you can see it says plus 16 minus 16, which is 0. So the discriminant is 0, which means I only get one lambda that works. So I have only one lambda, and you find that one lambda by saying minus b, that would be 2a. And that is how you solve a quadratic equation. When the discriminant is 0, minus b over 2a, and then we substitute the numbers. Minus b must be minus negative 4, so that makes it plus 4. That is further with 2 times 1, which equals 2. See, I only got one solution. The one we already knew would be 2. That's how I had created it, so it's not surprising. So it resulted in 2, but that means I only have one solution. I basically have only one vector to work with, and it's this one, e to the 2x, because I have set lambda to 2 now, since I found out that lambda should be 2. And then there was this problem that we couldn't rate the complete solution because it needed to be a linear combination of 2 linearly independent solutions. But the trick was to do it like this.
Look there is one.
Yes, e to the power of 2x plus c2 times x times e to the power of 2x. And maybe after the next break, if we have time, if time doesn't get lost in practice, we can prove that it is also a solution. It's actually pretty cool because you can prove that it's also a solution when you multiply by x, when lambda only has one solution. Then you can prove that it also works if you multiply by x. It's quite magical, but it does. So the two constants c1, 2 here are arbitrary real numbers, and here is the complete solution. That is the complete solution to that differential equation. So in just a moment, we'll take example 3, where I'll ensure that the discriminant becomes negative, and then you will have seen all 3 cases. So I don't know if anyone needs a picture before I erase it. Before I erase it, so you can see that this is actually easier than solving first order differential equations, because the only thing you need to do is solve another line. What makes it harder is not what I ask about in the exam, it's the proofs. So you need to be able to prove what I started showing today, that if y1 and y2 are solutions, then any linear combination is also a solution. And then you need to be able to derive the 3 cases. And of course, you should also be able to work through examples if I ask, because that is the most straightforward task. And in that case, it is a good idea to have prepared examples yourself.
So I don't like...
So if I ask, can you just show an example? Yes, I actually have one here I can show. It's a bit better for you than if I have to come up with something. There is something strange about mathematicians. They always think that what they have thought of is also obvious to everyone else. I've personally experienced, during an oral math exam, the teacher asking if I could solve this. Then you're faced with something that looks completely impossible, but that's because there was some clever trick you could use, which he knew because he came up with a problem. It's a bit unfair to ask that type of question in an oral exam, so I try to avoid it. Approaching the qualification. Last example before we go out and practice. Example 3. And it also says board 6. Now I need to come up with an example where the discriminant is negative. How do I do that? Well, I could do it like this. 2x squared plus 18. It must be equal to 0. If I move 18 to the other side, then we have minus 18. So this is the solution for when it says 2x squared equals negative 18. And then I divide by 2 on both sides. So it says x squared equals negative 9. And there are no real numbers that squared give negative 9. So it must be because I have a negative square root. This quadratic equation corresponds to a negative discriminant. I might be creating challenges for myself when calculating the discriminant, but let's just try. So I look at that equation and think, then this differential equation, which is called 2xy prime plus 0 times reach plus 18xy prime equal to 0. This one must have a characteristic equation with a negative discriminant. So now we erase what we used as inspiration for the task, and then we begin. What does the characteristic equation look like? That's always the first thing you need to do. You need to find the characteristic equation. It must have 2 lambda squared plus 0 lambda. It is the characteristic equation. Then we find the discriminant. It's b squared minus 4ac. Can you imagine how many times I've actually written this in my life? B squared minus 4ac. It's probably a lot of times. It's likely several hundred times. It's not so surprising that you can remember it soon. So let's plug in the numbers. What was b? It was 0. Minus 4 times a, which is 2. And then times c, which is 18. Mom, I knew it would be hard to figure this out. Oh, well, it's okay. So what is 4 times 2? It's 8. And 8 times 10, that's 80. And 8 times 8, that's 64. So 144 minus 144. So the discriminant is negative. And that means we know there won't be any real solutions, but there will be 2 complex ones. And what do they look like? Well, they look like this. Lambda 1 and 2. Is it negative b plus or minus the square root of d, all divided by 2a? And then we plug in the numbers. Minus b, that must be 0, because b is 0, so I don't need to write it. So I just need to write plus or minus the square root, minus 144, and then divided by 2 times 2, which is 4. Are you following along? Now the square root of negative 144. There's something about 12 squared equals 144, right? 12 times 12 equals 144. So this can be rewritten as plus or minus the square root of 144 times negative 1. It's better with 4. But the square root of a product is the square root of each factor individually. This holds true for real numbers. And the square root of 144 is 12. And the square root of negative 1 is the imaginary unit I. So therefore, it becomes plus or minus 12i. That gives us divided by 4. Ouch. Fortunately, 4 divides evenly into 12, so it gives plus or minus 3i. Are the 2 solutions complex conjugates? Yes, they are. For one is the complex conjugate of the other, as they are mirrored around the real axis, these 2 complex solutions. And if I were to write it more generally, it actually says 0 plus or minus 3i. And this number here was my alpha when I had the theory, and the number there is my beta. So now I have my 2 lambdas, and then I can plug them into the solution formula I wrote down for you. And it said that the complete solution becomes y equals e raised to the power of alpha times x times parentheses c1 times cosine of beta x.
plus 82. Multiply sine by beta x. And I know that my alpha is 0 and my beta is 3. Then just observe it. So I substitute e at 0. That was just 1. So I won't write it. E to the 0. That was 1. So here it says e raised to the power of 0x, but it was just 1. And then I need to multiply it by c1 times cosine of beta. But beta was 3. So 3x. And then plus c2. This was c1. I forgot to write a 1. And then multiply by sin. It is 3x. And then we have the solution. There it is. So if we just write it a bit nicer, it's simply c1 cosine 3x. Now it is c2 sine of 3x, where c1 and c2 belongs to the real numbers.
So now I have an example of all three in this case.
And next time, which will be the last time for the biotech students, next time, which is the last session for the biotech students, I will characterize the three solutions. What does that mean? What distinguishes the three solutions from each other? One is called an overdamped solution, and the second is called critically damped, and the last one is called underdamped. It turns out this can be used to describe how a car suspension system works when driving over a bump. So you can use this theory to design shock absorbers. It's pretty cool. I mean, if you think it's cool, and you do, otherwise you wouldn't be here reading about these things. You've probably had dreams about cars driving over bumps all night. But let's get out and practice the proofs. I'll be walking around helping you. Pair up as you usually do. Thanks for today.